Well, good afternoon officially on video. It's not quite so warm out as it was yesterday, but it's still nice and sunny outside. I guess the debate that I've read, and I haven't read much news on COVID-19 today, is will heat and humidity make it become less active? No one knows the answer to that question right now, but I think that's something that people would hope. But I'll just throw out there that in the budget meeting, we talked about a lot of interesting things, but something that did come out from the provost in an update right after that meeting was over with is that summer school is going to be run in this same fashion. So if you're planning on taking it, some classes may not run because if they have lab components, we're not going to launch new classes that have lab components that can't be activated. And I'm going to guess that would be Dr. Kelker's RF electronics class that he's been teaching year after year. Unless he figures a way that he can make it work, I don't see how it can work, though. Analog discovery, though, is amazing, so there's a lot of nice things you can do with it, and I'm really happy that I have adopted it actually quite a few years ago now. In the fall, though, they plan on returning to regular teaching, but don't really know for sure because, as our meeting today said, there could be a second wave of this whole thing that comes along at that time. That remains to be seen, but at any rate, I'm going to get started, and we're going to look at the mock quiz. I don't have to announce assignments being pushed up or anything because that's all happened. We did talk about when the second exam would occur. I don't feel like I need to officially come on board with that and make that final decision, but I think I got a response from one person saying that printing the exam would be no problem, and hopefully others of you will just confirm that with me so I know that that's going to work. You know, like I said, the other option is you would have to hand draw everything on your own sheets, and that's certainly possible, but I don't design tests that way. I generally design them to give you a workspace, give you some partial drawings and waveforms and block diagrams and stuff like that, but just let me know so I know I'm heading in the right direction with those plans. So this quiz, number 9, would be right in the pocket for what you're turning in homework today. So let's just take a look at it and work our way through it, and then we'll jump back into demodulators and then move into the phase lock loop. So one of the things that you would have if you were taking this quiz is you would have, and I'm going to be utilizing that in this quiz, you would have your tables. In particular, you would have the Bessel functions, and you would have the zeros of the Bessel function, and you would have this plot that I've got pasted in from the book. So we're going to utilize that as we work our way along, and this comes up in the second of the 2 problems on the quiz. So this first one is, I'm trying to think which homework problem. It's a little bit like problem number, what is it, 11? My mind is drawing a blank right now. I've got to pull up my solutions on my other computer. Textbook problem. Well, 11 has it in it. The one that got into it a lot, though, was 413. So it's a little bit like that problem. So we're given the form of a FM modulated carrier, and you know it's an FM modulated carrier because of the fact that you see the integral inside the argument of the cosine. So immediately you can start your brain whirling away saying, okay, I need to identify the deviation constant of the modulator, and that jumps off the page right in here as your FD. And then, okay, what is the message that we're applying? The message we're applying is a step function that turns on with amplitude 3 at t is equal to 0, and then turns off at t is equal to 4. and FD is 10 kilohertz per volt, and I'm assuming that the units on M, the message, is also in volts. So the first sketch that you have to make is just sketching what MV of T is. So that's going to come along, and then at 0 it's going to jump up to 3, and then at 4 it's going to shut back down again. Does anybody want to dispute that? I could be really creative and stop sharing my screen and let somebody else share their screen and then let my video capture that, but I don't feel like I'm up to trying that right now. But you can certainly tell me what you're thinking. This is correct, right? We're going to turn on at 0 and turn off at 4. So then if we want to get phi, we have to be able to integrate this. So we have to kind of go off to the side here and say the big deal is that we're going to have a rectangle, and that's going to integrate into a ramp. So we're going to be ramping up, and we have to take that into account. So it's going to be 3 times 10 to the 4th times 2 pi. It's going to be the slope of the ramp. So we know that we're going to ramp up, and what I'm going to do is I'm going to just sketch the ramp and then put some scale factors on there afterwards. I guess a big question is, what's going to happen when t is equal to 4? The input goes away at that point, but an integral is going to hold at that value even though we stopped giving it input, so it's going to hold at that value. So it's going to be integrating 3, and by the time we get to 4, we'll have integrated the 3 up to what? What are we going to be holding at when we reach 4? 12? Does that sound right? And if we combine that together with the other scale factor, 10 to the 4th and 2 pi, we'd have to get that exact value calculated out. But this is where I'm going to go off and pretend that I have my calculator. I opened up a Jupyter Qt console, which you can launch by just typing Jupyter space Qt console, and it will open up this just the terminal alone, and you can do commands inside of it. So I'm going to leave the 2 pi out of there, but I'm going to say we're going to go 3 times 4. That's, of course, is 12, but then we're going to go 3 times 4 times 1e4, which is our 10,000. So that's 120,000. So I could write this as 2 pi times 120 E3 is what we're going to slope up to, if we wanted to do it that way. Does that sound good by you? I realize everybody has a microphone off, but does anybody disagree or question that? Yes, exactly. Because that FD is inside of there. 2 pi times FD times the integral of the rectangular pulse there, which creates a constant, a slope, right? It'll be something like 3t on the interval 0 to 4 seconds, and then it goes away after that. So it's integrating that. It's a linear, because it's a constant value. And then when that was just simply 10 kilohertz. Yeah. And then I just left the 2 pi outside of that, but if you wanted to get that thrown in there, of course, we could go down here and we could throw the 2 pi in there too. So you'd have a pretty oddballish looking number. 753.98 e to the 3 radians would be the phase. So the phase is just ramping up like crazy. I mean, if you were visualizing this on the unit circle, plotting it like a phasor drawing or something, the phase is just winding up, way up there as time marches on, and then it stops and then it holds. And that's the nature of phase modulation. I mean, the carrier has always got the linear phase due to the 2 pi FCT, and then we get the additional phase deviation. So in this plot, though, you were supposed to plot the phase deviation, and that's just due to the modulation. So that is, what I've done. Phi of t is just due to the modulation. Okay, part B says, what is the frequency deviation, peak frequency deviation? Well, the message is instantaneous frequency, or the frequency deviation as a function of time is just Fd times m of t, right? That's just the frequency deviation, or the derivative of the phase deviation divided by 2 pi. So the peak deviation is when the pulse turns on and runs for a duration of 4 seconds. So it's just going to be 3 times 10,000, or that would be 30 kilohertz, right? 3 times 10 to the 4th, or 30 kilohertz, because we apply 3 volts times the FD, so that's the maximum value, and that's sustained for 4 seconds. Then that deviation goes away. The carrier returns back to its undeviated value. But the phase has already been spiraled up there through that integrating action, and that doesn't change. It stays put because the integral, it has memory, right? It integrates up and then it holds. So I'm going to move on to number 2, unless there's any other question on that. Hopefully you can see from a problem like this, there's various different questions that I could ask. I could ask a lot of different. I ask questions here that are pretty straightforward. I could ask questions that were somewhat, I wouldn't say devious, but kind of trying to trip you up. So I could have said, sketch the phase, the total phase deviation, in which case then you would have had to include the 2 pi Fc times t in there as well. But I didn't do that, and I probably won't do that either. I'm just saying, though, that could have been another way to do it. Or I could have asked you to draw a picture of the instantaneous frequency of the modulated carrier. That would have been, whatever Fc is plus, so I could call it F subtotal. Deviation would have been Fc plus Fd times m of t. So if the carrier was, say, 1 megahertz, the carrier would be deviated up by 30 kilohertz for 4 seconds, and then it would return back to its 1 megahertz value. It's unfortunate, but for those of you that were taking the lab, if you would have been in the lab, you would have had a really good hands-on with this with the equipment. If you have an analog discovery, you can still play with it at home, but I know not all of you do. It's just develops a lot of good feelings about that. Likewise, this number 2 problem where I say it's a VCO, that was going to be developed in the lab with the real equipment, because we can turn the function generator into a VCO by putting it into an external modulation mode, which is what I have written into the lab experiment, where you set the center frequency of the VCO, as in the center frequency of the function generator, and then you apply a control voltage to the back port of the function generator, and that allows you to then deviate the carrier away from its quiescent or center frequency. So in this example, I said the center frequency of the generator was 100 megahertz. The deviation constant of the modulator is 1 kilohertz per volt. And then we're going to apply sinusoidal modulation of this form. So an amplitude A, and this is 1 kilohertz, a 1 kilohertz tone. And we're going to set the amplitude of that to 5 volts. So we're going to be putting a peak frequency deviation on, in this case, of FD times A, which is going to be 5 times 1 kilohertz, so it's going to be 5 kilohertz. That's not a question I'm asking here, but I do say find the strength, find the modulation index, and then find the strength of the sidebands that are either side of that carrier, that 100 megahertz carrier, at 100 megahertz plus and minus 6 kilohertz. So first off, what is beta? This is something that you could rederive, but it's better, I think, if you just have it committed to memory. We've talked about it a number of times. In the case of FM, remember it was FD, for sinusoidal FM, FD times A over FM is what that comes down to. Why is that FM in the denominator? We can go back up here, I don't want to necessarily scribble that away, but if we're putting, for modulation, a cosine into the integral there, when we integrate that cosine, we're going to get a 1 over 2 pi times FM that comes out of there. So what nets out of the integral is going to be something along the lines of FdA over Fm times the sine of 2 pi Fm t. So right there, that is our beta. So FdA over Fm. Deleting that because I want to have space for the next part. So plug numbers into here. And that's going to be the 5 kilohertz that we already have. And then FM is 1 kilohertz. So beta is equal to 5. So now we want to find the strength of the sidebands at plus and minus 6 kilohertz about the 100 megahertz carrier. So this is where we need to go to the Bessel function table to get that information, because we know what beta is, and we're wanting to know what the second harmonic is. So n is going to be equal to 2 in what we're looking for in the table. So I'm going to jump over to that table right now, and I'm going to go look for the appropriate column, but I see beta running across the top, and I'm just looking for beta equals 5, which is what we have. And then I'm looking at which harmonic we're interested in about the carrier. We're interested in the second harmonic because that's going to be plus and minus 6 kilohertz. So I come across, and this is not going to work for me. I was going to try to use the highlighter for a change, but it's not working. Just do it this way. So that says the Bessel function. So this is actually J2 of 5 is equal to 0.047. So that's going to be the strength that we need for our problem. So I looked on my TI Inspire calculator and I didn't see Bessel functions were available on there. So no matter what kind of calculator you have, you're going to be needing to use a table like this to work a problem that requires this information. So next week's quiz will move on and have some things with bandwidth and the other types of calculations that we've been doing since then. So I'm going to move over to back to the quiz. So I'm going to find those strengths to be strength of the sidebands to be 0.047. So I have to kind of draw my spectrum picture here. And I'm going to draw this as a single-sided spectrum. Let's see, we're at 100 megahertz, so 10, let's see, I'll just write it out. This is kind of zoomed in, but this is and if I drop 6 kilohertz below or plus 6 kilohertz above, then I'm looking at there's going to be a sideband sitting in here. There's a sideband here, and here, and here, but the sideband we're looking for is the one at 6, which is the 0.047. And let's see, what am I missing on that? Am I missing a factor of 1/2? I have to go double check myself just to make sure I haven't screwed up there. What does anybody think? Am I missing a factor of 1/2? Should each of the upper and lower sidebands be 1/2, even though we're talking about a single-sided spectrum? I'm going to go over and look in the notes to make sure I haven't messed something up. So I jump way back up into here when we first did the expansion. This kind of gives us the answer right here, though. The carrier, which is 1 in this case, sits out in front. And then the expansion looks like this. We just have Jn of beta, and the harmonics in here will have n is equal to +2 and n is equal to -2, and that's going to give us the sideband. So I think we're good to go at this point. When we actually do the power calculation, though, due to the sidebands, then we had the 1/2 factor in there. Okay, so I'm going to jump back over to the quiz, and then we'll eventually come back into the notes. So I think that takes care of this, 0.047. Now what I could have done, though, is I could have put a factor in. Whoops, didn't draw that right. I could have put a factor in here. I could have said AC equals 100, and let's say, and then I'd have to multiply these Bessel functions by 100. But in this case, AC just equal 1, or equals 1. I guess this stems back from me saying I want the strength of the sidebands, so that's what we want. I could have added the word single-sided, and I probably will try to do that in the future to make sure it's clear that we're talking about the single-sided spectrum. Okay, the second part, or part B, says find the second smallest value of A that makes the carrier component of the spectrum 0. So I've given this quiz before, and I know this is confusing. Second smallest value of A. So remember the Bessel function zeros. Well, first off, let's just remind ourselves that this is the formula for beta. So if we go back and look at the Bessel function tables, now I'm going to get myself confused. I'm looking for the carrier component. So we're dealing with the carrier component here. So the second smallest value of A, since beta is equal to A times Fm over, not Fm, but Fd. In this problem, that ratio Fd over Fm is constant, so we're just wanting to find the second smallest value of A that will make the carrier go to 0. So we're looking, the first value of A is going to be somewhere right in there. That's our 2.4048. The second value is sitting out right over here. So that's the second smallest value. So we're looking for beta equaling 5.5201 in this particular scenario. So if we solve for A is going to equal what? Fm over Fd times 1 over, no, times beta. Is that right? So that's what we're looking for in the value that we're going to plug in for beta. Got this wrong. Yeah, the value we're going to plug in for beta is that value, 5.5201. That's the second smallest value of A, because the smallest value of A would be obtained when we use beta equals 2.4048. So the second smallest. Anybody confused by that language? .5201, so I'm going to move this onto the quiz, so I'll be able to post the quiz. Trying to get this written on here though. Which implies A has to be equal to Fm over Fd times beta second. And then I'm going to go, just do it this way, I'm going to calculate it again. So Fm was 1000, Fd was 1000, and beta is 5.5201. So that's the answer, 5.5201. So that's the second smallest value of A that will make the carrier go to 0. Good? I'm ready to move along, but I'll just go back and refresh your memory of something that we did yesterday or 2 days ago. And we were looking at building a modulator. Actually, it's going to show up in my very first example here, so let me just do that right in this example, and then I'll be able to do it. So just going to make sure I don't forget it. 2.4048 makes the carrier go to 0. And that was the amplitude of A in this particular case. The way I built up this modulator was with cosine, and I just made the amplitude of it be beta, because that's the way it works out in this particular case. So I'm just going to comment this out, 2.4048, and then I'm going to put in here 5.5201 and create that waveform and look at the Bessel function spectrum, and sure enough the carrier is null to 0 once again. The spectrum is wider because beta is bigger, but we still have the carrier going to 0 at that point. So that's just a numerical simulation of it, is what it comes down to. So I'm going to move back to the notes now unless somebody's got a question, and then I'll post this up sometime after class. Okay, where we left off last time, we had gone through the discriminator, the theoretical concept of the discriminator, and then we were looking at a complex baseband discriminator, and that was motivated by the fact that we could approximate the derivative through what's called a first backwards difference, where we're going to take the present value minus the previous value, and that would be a simple means of differentiating less the scale factor that comes from dividing by t, the definition of the derivative. So we'd get an approximation to the derivative with a scale factor of the time separation, and that would be a means of getting at a discriminator, ideal discriminator type solution through this approximation to the derivative. So that's the complex baseband discriminator, and I talked a little bit about the math of it last time. So in order to model this complex in the complex envelope form, we have cosine of phi plus j sine of phi. This is what we would be recovering from an angle modulated signal. We're interested in getting our hands on the derivative of that argument. And we can do that by looking at in-phase and quadrature signals, the complex envelope, which I've got expanded out here, and that involves xq and xi, and we take the derivative of that, of the arctangent, we get this. And I don't have this committed to memory. I have to look in a math handbook, but I don't know if this is in the back of the textbook or not, but I'm sure you remember seeing this in calculus at some point. So this is the derivative that we need to approximate, and what we do in the discrete time domain is approximate the derivative for xi prime and xq prime with this backwards difference. So we're just going to use a single difference. I just want to point out to you that that if you're interested in a more detailed derivation of that, we can jump over to the COM lab, and in the software-defined radio lab number 6 is where I have a more detailed derivation of that. You have to drop quite a ways down into the lab itself. So I have a review of FM modulation theory in here, and then I'm getting into complex baseband discriminator, also known as a quadricorrelator, and go through the same argument that I just had in the notes. But then in here I do more of a detailed analysis of this discriminator and how we're going to implement it in the discrete time domain. And I kind of carry that along and eventually make an approximation in here and come to the conclusion that this simplified discriminator is not a constant slope. Instead, it has this sinusoidal response. So it's only good in a narrow region, and I'm going to demonstrate that here in the Python simulation. But in this region here, it approximates the ideal discriminator when we're trying to demodulate FM from a carrier located at a nominal baseband carrier frequency of 0, which would just come about in a software-defined radio application. So I'll just leave that up there. Those of you in the lab, you'll be doing lab 6 with some test vectors unless you buy your own $20 radio dongle. But I'm going to jump back over to the code. The code that I have in the notes is MATLAB code. I left it in here because when I started using Jupyter, I decided I'll just leave the Python or the MATLAB version of it in here. So this code here is exactly what I have in Python, and I'm just going to look at that so I can play with it more interactively. So here I generate a complex baseband single tone modulation. Last time I talked about a general way of doing it using cumulative sum for any type of waveform. Here I'm just taking the special case of sinusoidal FM, a complex baseband, and I generate that directly right here. This is the message, which is a cosine, and then this is actually the integral if it was FM, but it's cosine if it's phase modulation. And then I also have hanging out here another term so I can shift the center frequency away from 0 to maybe make it some low frequency carrier. And I'm going to demonstrate what that does here after I run it with FC equals 0. So I'm setting the sampling rate at 50 kilohertz. I just generate this again. I generated the spectrum with beta of 2.4048. I'm just using that as a test because it's convenient, and I know I'm there when I can see that the carrier is nulled. And then up here, I compiled this by doing Shift-Enter on this cell for the discriminator. And now I use it. I run the complex baseband signal into the discriminator. It's expecting a complex signal near 0 hertz. And then I have YD, so when I go ahead and plot YD down here, you can see how nice it looks. It's coming out like the input. I mean, it's coming out like the way we'd expect it. Now, the caveat is we're operating in the linear region. When the input deviation relative to the sampling frequency starts pushing to plus and minus 1, we're going to have an issue. And to see how that builds up, suppose I start by moving the carrier frequency up to 1 kilohertz. My message is at 1 kilohertz, so if I go do that initially, I'm going to see now my spectrum is just shifted up, not up and down because we're using a complex sinusoid to shift it, so we're going to just shift up by 1 kilohertz. And if I look at the output under that scenario, we'll see that the output is now starting to shift up with a DC bias, and that's corresponding to the fact that the carrier is now not centered on 0 anymore. So let me just kind of make this a little bit more intense. I'm going to shift it all the way up to 5 kilohertz. Spectrum will shift up to the right by 5 kilohertz. Modulator has no problem. It's just can move it to wherever I want to move it. But now with the discriminator centered at 0, this output is shifting up higher and higher in amplitude, corresponding to the fact that the discriminator is saying, hey, the mean frequency is shifted away from 0, and it's going to put out a DC value to reflect the fact that the input is averaging a instantaneous frequency around 5,000. But remember I said it's got a linear region, and we're getting very close to being out of that linear region. So if I shift this all the way up to 10 kilohertz, and now it's going to be kind of off to the edge, because 10 kilohertz is way out over here in my plot window. But now when I go look at the output of the discriminator, we've hit the edge of the linear region. We're now bending back down again, and that's exactly what this lab said would happen. When we hit 1, we can't put an output out greater than 1, and it starts increasing the amount of distortion here. So that's exactly what we're seeing. It's getting very distorted in here. So it's got limitations, is all I can say. I have used this in consulting work before, though. This quadricorrelator, complex baseband discriminator, I used it a bunch when I had a master's degree student use it on some research many years ago. And I first read about it in a paper on cellular telephony applications or data applications. This goes way back in time now. Most of you are too young to appreciate this, but at one time cell phones were used only for voice communications. Data was not even possible in the very beginning. Then they started adding data services. They did things that were very limiting in how much data you could push through the cellular network, but they started with some simpler schemes, and I was involved with a project where I was studying interference and issues with voice communications and data on the same network. It's not very sophisticated sounding anymore because things changed a whole lot, but if you go back in time, there was a time when, and most of you should be able to remember this, there was a time when you used to get minutes of talk time, and then you also paid for data minutes or data kilobytes or megabytes or whatever. The more recent changes in plans and everything, now talk is unlimited and data is regulated by your service contract. Some of you might have unlimited data plans, I don't know, but can anybody, I'm just curious for somebody that might want to flip their mic on or talk to me on Slack. Does anybody remember when you used to get a quota in minutes of talk time? That could be. I didn't have a phone then. I didn't have a cell phone way back then. I worked in the industry, but I never had one. Never had a phone until my sons went to college. That's when I got one. Yeah. You guys, what do you value more in your wireless device? When I've taught the Maker Electronics class for the general ed curriculum, I have the first paper is talking about what does wireless technologies mean to me, and I've learned a lot by essentially interviewing students, and most of you like data better than voice, is what I've learned. Okay? But you don't necessarily do that much talking on it. You're doing data, right? Yeah. So I could see that coming a long, long time ago, but it took a while because of the mentality of the users was, we just want to talk. We want to do it wirelessly. So I find it interesting only because, things always change, right? And this was something that had to go through that change. And I was really glad when they stopped charging you, setting a limit on your voice minutes, because I never used them. I had my phone, when I started using it, was mostly for data too. I didn't really want to talk. My father, who passed away about 2 years ago this week, actually, 2 years ago this week. In fact, now that I'm thinking about it, it was the week of Easter, so it would have been Tuesday. Yeah, it changes every year, my wife's pointing out, but it was this time of the year, though. It was in March, actually, then. But at any rate, he's one generation older than me. He used his phone for data and texting and everything, but voice was still something that he loved to do, and he was of the generation of the voice users on the cell phone. And I think that's kind of related to age from what I've seen. Okay, back to looking at some other discriminators. So I spent that much time on that quadricorrelator complex baseband discriminator because those of you doing Lab 6, you'll be using that function, and that function is actually built into the module in Scikit called RTL SDR underscore helper, and the RTL SDR is the low-cost $20 software-defined radio receiver that gets used in that lab. So you'll be using that as part of the FM receiver that you'll build in software. Some other circuit implementations that are used for FM discriminators would be this simple low-pass filter, or it could be a high-pass filter or a band-pass filter, and this is called a slope detector. So we're going to talk a little bit about slope detectors, and I've got a simulation of that. This is not so common in software because we have other ways of writing algorithms to do it, but in circuit implementations and in RFICs that maybe are decoding analog FM messaging or even data, things related to the slope detector are still of interest. And the basic idea of the slope detector for the high-pass filter goes like this. You've got the FM signal, which is deviating back and forth in here, instantaneous frequency changes with the message, and then you pass it through a filter that has some slope, some gain slope across that passband. So your mind should say instantaneously, I'm going to see an amplitude shift as a result of having that gain slope on the filter. The filter has time constants in it because it has L's and C's or R and C or whatever, but the time constants of the filter are very tiny compared to the message frequencies. So the message is moving slowly and hangs out long enough that the filter can settle to its new output value because of the ratios of the carrier frequency to the bandwidth of the message. So it responds essentially instantaneously. So the amplitude fluctuates up and down. And then you just slap an envelope detector on the output there, and so what you've done is you've converted FM to AM by having that amplitude slope. In broadcast FM, they use an IF frequency of 10.7 megahertz. That was in the radios from Lab 4. also 455 kilohertz for the narrowband version. But it wasn't too long after FM became popular that a circuit ID known as the balance discriminator came into being, and the balance discriminator sets up a pair of bandpass filters, one set above the other, and then when you use those in combination, you can get a wider linear region for your slope detecting. And this is an example of what the balance discriminator looks like in an RF kind of an implementation. The radio boards that we build in that Maker Electronics class have an FM receiver along with the AM receiver. The FM receiver uses exactly this arrangement to get its discriminator to work for FM. Another type that's been popular in RFICs is the quadrature detector, and that is what is used in the Lab 4 radios. So they have, those RFICs have had this quadrature detector inside of them. The capacitor and the tank circuit were supplied externally to the IC, but then there's a multiplier in there. So, and then the output of that is a low-pass filter. So a little bit of math behind that is, if you model the FM modulation like this, and I think I don't know how I forgot this. I haven't seen this, but this is an error. There's a cosine missing in there. So angle modulation, or maybe I had sine in there, and then you look at the action of the tank circuit, and that is like differentiating. And when you take and multiply that times the original signal, then in the end you're able to extract out the derivative of the phase term. I'm not dwelling on this too much. This is kind of old-fashioned in a way too, but it's just representative of what people came up with for low-cost FM demodulators in RFICs that would be used in portable electronics and so on. Next up is the phase lock loop, but before we do that, we're just going to take a quick look at the slope detector. So here, I tried to build up the high-pass version of it. So again, I kept the sample rate at 50 kilohertz. I just put up a carrier at 8 kilohertz as an example. I used the SciPy .signal to design a Butterworth high-pass filter. I could have used my functions in IIR Design Helper that you already experienced in Project 1, but I just did it this way. I got fifth order, and then if I do Shift-Tab on this, you can see I get to set the cutoff frequency in terms of the Nyquist rate or folding frequency. So you have to scale it by 2, and then you set your cutoff divided by fs, and then I set the type, because the type is defaults to low. So if you want high pass, then you have to type the word high pass in there. So I go ahead and do that. Take a look at what that frequency high pass filter response is, and then there's a homework problem, and I don't remember now that I assigned it, but the idea would be, where is this most linear? So if we drop down at about 7 kilohertz with our carrier, we're landing kind of in the linear region of this amplitude response. So I generate a frequency modulated signal as cosine. The carrier is at 7 kilohertz. And there's the message again, the cosine. I've got a message frequency of 200 hertz. This last line, complex, I'm going to look at in a second. It's something I just added about an hour ago. At any rate, look at the spectrum of that FM signal up on a carrier, and just picture if I zoomed in on that, we'd see all the spectral lines. And now what we're going to do is pass that through the high-pass filter. So here it goes through the high-pass filter, and I'm having it create several plots. Let's see if I can get these right. FM signal goes in, constant envelope, no fluctuation on the amplitude, comes out of the high-pass filter here, and lo and behold, the gain slope of the filter has converted the signal to have envelope fluctuations. Now this signal still has FM too, so we're seeing amplitude fluctuations due to the message. If I was to look at the frequency deviation inside of here, it is still FMing away instantaneously. But now I can envelope detect that, and here I just simply use the sine function to create a clipper, and then I could send this into a low-pass filter and block the DC if I wanted to, and then I'd have the message back. But this, for me, was far enough to just verify that, yes, I've converted FM to AM and I can envelope detect it. Now, another thing that we could do, and John is in the real-time DSP class, so he's got this in a homework assignment right now to do a real-time implementation of this on a microcontroller board. But we can actually do something else with this. We could decide to make this signal complex. So I'm just not describing how I would do that. You might do that with the Hilbert transform and then making an analytic signal. So here I've just made it a complex sinusoid with angle modulation. So if I go take a look at that spectrum, which is what I've done here, of the complex signal, it's complex, but it only has one sideband because I've located it on plus 7,000 hertz. There is no signal at minus 7,000 because it is a complex sinusoid. So now the envelope of this signal will be the exact AM envelope. And let me just show you how easy that is. If I come down here and just take the absolute value of that complex signal that's producing that spectrum, and I'll just rerun it again so you can believe that it's happening. There's the output. The output is the blue. I just plotted the underlying message scaled by 0.1 just so you can believe that it is the real deal. It needs a DC block on it right now. But this is just a matter of taking and finding the envelope of the complex signal, and that's just the absolute value. So that was just a little thing I decided to throw out today. If it's confusing to you, don't let it bother you. I just did it kind of for the benefit of John, who's in the real-time DSP class, to know that, hey, it does really, really work. Other than that, I'm ready to go into phase-locked loops. Does anybody have any questions? Of course, I can move this signal around. I guess a curiosity that just hit my mind is maybe you're saying, what happens if that's negative? So what if I did this? I made F naught be negative in here, in the complex signal. Go down and look at its spectrum. Now it's hanging out down here. Doesn't matter. It looks the same. So complex signals don't propagate through space like that, though. We only send a real signal. We'd have to have two emitters, or two coax cables or something like that. But if we signal process them, then we can take advantage of that analytic signal idea that we looked at a while back when we were studying single sideband. So I'm going to be set up here when I come back over here from the notes to look at phase lock loops. And I've got some phase lock loops inside the module of Scikit DSP-Com. It's the synchronization module, which this whole module has been kind of the focus of my class number 3 that I teach from 8 to 10:40 on Wednesdays, the phase lock loop synchronization class. So there's a bunch of functions inside of there. We're going to use just a couple of them here. So phase lock loops have a lot of applications. We're going to start angling into it as an FM demodulator, but then we'll see how indirect frequency synthesis can be done. We can develop means of recovering a coherent carrier and build a carrier synchronization system for double sideband using a phase lock loop to lock on to the carrier. We can lock on to residual carriers. We can lock on to pilot carriers. They have a lot of interesting applications. And it was invented, I was just reading this in my class, I think there's a guy in France that invented it, and I think it was 1942 or something like that was when it was invented. Okay. Right, for color and the audio was FM. I'm pretty sure they did. So that brings you to something that aggravates me about HDTV. I mean, I know with analog TV, there was a subcarrier, you instantaneously demodulated it, you demodulated the video from the vestigial sideband scheme. The voice and the image were always in sync. But I find with the digital standard now, that doesn't happen all the time. And I find it annoying when the lips and the sound are not together. And I always ask this in my class, usually not right at this point, but does everybody observe that at least once in their life? Watching an HD program and see that the sound and the video are not synced. Maybe it doesn't bother you though, so that's why if you haven't seen it before, you just haven't looked for it. Okay, so here's the block diagram of the phase lock loop. I don't teach my phase lock loops class very often at all. But this whole semester I've been looking at this block diagram and variations on it constantly. This is a challenging subject to really drill into, and we get fairly detailed in this class too. You will have a simulation kind of problem that's embedded in a homework assignment that's coming up. So you will be playing with it. You'll be using the models that I have in that synchronization submodule of Scikit DSP-Com. So you'll just be doing like a lab experiment effectively in software. So the main elements of the phase lock loop are a phase detector, of which the input signal goes into. So this would be our received FM signal or received some signal that we want to lock onto. We'll see other applications where in a synthesizer that input is actually from a stable crystal reference that we're trying to do what's called indirect synthesis. But that'll be an application we'll get into later. We do have some homework problems on that too. At any rate, the output of the phase detector is an error signal, E sub D. That drives a loop filter. The loop filter drives a loop amplifier, and then a control signal, which is this EV, the VCO control voltage, moves the oscillator up or down in frequency and then also in phase. And typically it's really a minus sign in there in order to make the loop lock with negative feedback. So the VCO will try to track the input frequency and phase of the signal and forms an estimate. So this is the way the model is generally put together. One is cosine, the other is sine, and that's because when the when the phase lock loop locks, the two sinusoids are in quadrature because we're looking at the error signal being the sign of the phase difference. So this is very important. And some of you have had control systems. Chris, who I'm not sure he's on. Can anybody? I'm not looking at that screen. Do we have everybody here or not today? I haven't heard his voice, so he took control systems in the fall. Some of you will probably take control systems next fall if you're juniors right now. But you learn about feedback control systems. So negative feedback is what it takes to have a stable system, and we're going to see that in a few moments here before class ends today. So frequency error is actually the derivative of the phase error, since they're related by derivative and integral like that. So what we're trying to do in reality, and the notation here is different than what I've been using in my PLL class because I'm using different sources, but the whole idea is to get the error to go to 0. And that means then that the VCO is producing a phase estimate, theta of t, that matches and follows phi of t at the input. So when we back up and look at this control signal over here, that will be effectively the derivative of the phase, so that will be in proportion to the frequency, and we're going to see that here in just a few minutes. But the control voltage on a phase lock loop will be in proportion to the instantaneous frequency of the input signal, subject to some filtering action that goes on in the loop itself. So to get the math worked out here, we have to go step by step, kind of work our way around the block diagram, and then literally close the loop. I say that because that's what you're doing when you set up a phase lock loop. You close the loop. In lab number 5, there's a phase lock loop experiment actually that you're not going to be able to do because you're not going to be in the lab to do that, but you build a first order phase lock loop, and closing the loop means you're connecting all the wires in order to bring this thing full circle. So closing the loop means you're connecting it all up so that now it's going to be something that pulls in by itself. It locks up all by itself. So the voltage controlled oscillator needs to be characterized in formally. So it produces an output frequency, a quiescent frequency, which is generally set by either a bias voltage at the input to the VCO and also in combination with some characteristic of the VCO. It might be there's a tank circuit in there, and the tank circuit has got a fixed capacitor and a varactor diode, so a variable voltage capacitor in parallel, and the tank circuit natively has some quiescent frequency. Generally, we make the quiescent frequency match that of the signal that we're trying to lock onto. And then the varactor diode allows you to tune the tank circuit, and you might do some fine-tuning of the quiescent frequency with an extra bias voltage out there, so that control voltage comes along and can be used to also bias the varactor diode in the tank circuit to center the VCO on a particular frequency. This is thinking in terms of an analog solution. There are digital oscillators too, and they're sometimes called NCO for numerically controlled oscillator, or another name that's probably the most popular name today is DDS for direct digital synthesis, and that's the term I'm using in my phase lock loops class for the digital phase lock loops that we've been studying since about the midpoint of the semester. But the bottom line is we do have a relationship, though, that the control voltage is going to directly cause deviation in frequency at the output. And we had the examples of the VCO in the quiz today. So we're saying that there's a gain constant kV. It's no longer called KD like it was in the quiz, because if it's a VCO, the more appropriate term is capital KV for VCO gain, and then the control voltage. And that will give you the instantaneous frequency, or integrating both sides, it gives you the phase. So with that block characterized, now we can go forward and kind of work our way around the loop, writing an equation. And I'm going to try to go fast enough that I can give you a quick demo. So the phase detector, we can linearize the loop, and that's what we're going to do. We're not going to linearize the loop. We're going to look at it in a baseband sense. So in baseband sense means that the input contains T of t, and the VCO output contains theta of t. Mathematically, modeling like this is just fine, but if you take a physical phase lock loop, you cannot touch that theta of phi of t or the theta of t, because it's an inherent component inside the argument of the oscillator oscillating the waveform itself. But we can still mathematically say those signals exist inside the argument of the cosine and the sine respectively, and that's going back up to where we see them sitting right inside of here. So we just want to treat it that way for right now. So this is the baseband model, and the loop nonlinearity is what I already identified up here. It is the sine, and then it has to do with the constants that come about when we take XR times EO. We're going to get 1/2 ACAV times the sine of the phase difference. There is a double frequency term that's going to be present when we do that multiplication, but we're ignoring that for the time being, because the loop filter is going to be able to remove that, or at least in most instances it can. It becomes an issue in certain types of designs, but again, I don't want to get too cranked up on that right now. So we have that sine nonlinearity in there. So now we can write a composite loop gain as 1/2 mu ACAV KD KV. So those are the gains working all the way around the loop. This is from the phase detector, and this is from the VCO. So put those together. Then we can write the VCO output as KT, the overall gain, times the integral of sine. And here what I'm doing is, initially, I'm going to do what's called a loop filter that is just a wire, so its impulse response is 0. So initially, we're going to consider the first order loop, which doesn't have a filter in there, so there is no f of t. So we crank that around, and we just have sine of the phase difference, and then we can rewrite that in terms of its derivative to get the instantaneous frequency. And then, kind of somewhat of a confusing factor, we're going to define psi of t as the phase error. So this is the phase error, and we're going to make a substitution then and write things in terms of psi of t is what we're going to do. So we have that is psi of t, and then psi of t is phi of t minus theta of t. So ultimately, this is what we have governing the first order phase lock loop, and this is a first order nonlinear differential equation. I say nonlinear because it has the sign of psi in there as opposed to psi all by itself. So this takes you down memory lane, I guess, from when you had differential equations, you would have seen some nonlinear differential equations. And they were not the most pleasant things to have to solve. But this is a first order one, so solving it is not that hard. It's stable when it's in equilibrium. So I'm out of time right now, so I'm going to have to pick this up again next week. But equilibrium means that it can stand still and not feel like it has to go hunting around and for another stable lock point. So the stable lock point is going to be when d psi dt is equal to 0. That ends up being the stable lock point. That's when the phase error is driven down to 0. So, or the frequency error, I mean, is driven down to 0. So the stable lock point is so, and this is what I have to get into next time, means that if it tries to increase, it's driven back down again. If it tries to decrease, it's driven back up again. So it's like magnets that are being attracted to each other, north and south poles. It will stay attracted at that point, and if it tries to drive off, it's going to come back to that point, because this point, let's say over here, I can't get my finger to get that to go. That's the unstable lock point. If it tries to sit there, a little bit of noise or something will jerk it, and it will just fly off of that point, and then it will go find the stable lock point. I'm going to have to ramp all back into that next time, but I'm fine with that because this is something I want you to get understood. But let's just do a simple first-order loop simulation. You'll have an idea of what it can do. I'm going to put in baseband right now a phase that is a step, a ramp actually. So it's a phase ramp, which is equivalent to a frequency step that's going to turn on at 0.5 seconds, and then at 1.5 seconds I put in a negative phase ramp, a negative instantaneous frequency of 12 hertz. So I'll go run that through my phase lock loop function PLL1, which takes as its input the input theta that's going to come from the input signal sampling rate, the type of loop, loop gain kV, and then this Fn is also related to kV in the case of the first order loop, but eventually we'll do other orders of loops, so I'll just run that. And then I'm going to look at the control signal coming out to drive the VCO, and what we're seeing on the VCO control voltage is it is following the instantaneous frequency of the input, because I jumped the input up at 0.5 seconds from 0 hertz to 8. So that's a phase ramp of 8, 2 pi times 8 radians per second, but in terms of instantaneous frequency, it's 8 hertz. At 1.5 seconds, it jumps down by 12, which is 8 minus 12 is minus 4. So there it hangs out. And we'll look more at what's going on here. There's the phase error psi as it jumps up and jumps down. And actually that is that's the phase error that was shown over here. I'm going to have to get into this more next time. Next week's homework, though, doesn't cover phase lock loops yet. Daniel in the lab is planning on doing something with phase lock loops, and he might just be using the simulation software. He didn't really tell me, but he said you're good through Wednesday, because he wouldn't be getting to phase lock loops in the lab until late Wednesday at the earliest. If you were really building one of these, you would be hooking up test equipment to do it, though. Right now in my phase lock loops class, they're doing a phase lock loop experiment using real-time DSP and using Pi Audio Helper, another module of Scikit DSP Com. So they're actually making a digital phase lock loop. They're using the analog discovery to create the waveforms and create the FM signal and demodulate and just play with some of the properties of the loop, all in software, but running in real time. So it's not a simulation, it's actual hardware software combination running in real time. I think this is a good stopping point because I can't get the details down in just a few minutes, so we'll have to leave it at that. And get your homework papers submitted to me on Slack, please. They're easier for me to grab that way. And carry on. No project to work on, so you can just work on homework and start trying to read more about the phase lock loop, so you'll be receptive next Tuesday. Yeah, as soon as I sign off here, I'm going to sit at this tablet and get it processing. My problem is, as John has pointed out, I process on my tablet, and then when it gets done compressing, then I push it up from the tablet, but then I usually go to a different computer and wire it up, put the link in, and I've been forgetting to do that. This might be done around dinner time, let's say, and then I say, oh, after dinner I have to go put the link in. I've already pushed it though, so if you're really excited, it might already be pushed up there before I get the link. It'll be pushed up before the link is done, I can guarantee that much. So. Okay, yeah. Okay, anybody else got anything they want to say before I go back to daily? Exam 2, let's just go back up over here. The earliest would be here. I doubt it if anybody's going to want to do it then. I'm thinking this would be a good day, or I've also said the 30th. We're going to finish the semester off with going through Appendix A, which I can do in about 3 days' time. And then you'll also be ramping up on Project 2, and you'll turn in Project 2 when you come to take the final, which I think is on Thursday, the 14th. Project 2, like I've said, is much, much easier. Everybody is always worried that Project 2 is going to be so hard, but it actually ends up being very easy. But the only way I can prove it to you is by having you work on it. No one will believe me until they work on it and see that, oh yeah, that wasn't too bad. But it happens. Right now you're gun shy. You don't want to tackle something that you think is going to be hard. But I think actually you get smarter and you'll be more comfortable with Python. But it's a pretty exciting. You do some pretty high level stuff though. Some pretty powerful digital mod and demod stuff that you get to do. And again, you're going to use the same audio files, only now you're going to be sending digital information. You're going to be converting it to ones and zeros and then recovering it again. So it'll involve the PCM encoding and decoding, but wrapped inside of it will be digital modulation and demodulation and some pretty high order modulation along the lines of what cable modems use. They use pretty high density modulation, and LTE does too. So LTE uses the same type of modulation known as quadrature amplitude modulation, which I'll be explaining. Okay, yeah, I'm not sharing my screen anymore, so let me share my screen and you'll see what I was trying to say. Okay, let me just go back to this. So the earliest would be the 23rd. I'm thinking we're going to be opting into the 28th or the 30th. Last week of class, regular class meetings is here, and then the final exam is probably on Thursday, the 14th. So that's my plan. If anybody wants to start casting their vote, that's fine. This is the, if you actually go up and look on assignment. Let me see. Got to get out of this class though. Go to the other class. This assignment right here. Now wait a minute. My brain is already racing ahead because I'm thinking of something else. I'm one assignment ahead. We're on 9. So this is where I posted it. This is on next week's assignment, where I was proposing these dates. So I'd like to start getting some feedback. And Chris, I don't think is here today, but maybe he is. Yes, I haven't heard his voice. He would be a person that would likely chime in to say make it later than earlier.